So these are nothing but the lead, lag compensators or lag lead compensators. Okay, so does anyone take a screenshot when the maximum members were present? Okay, when the maximum members were present, take a screenshot and send it to me. Okay, now so I'll discuss about the compensation techniques. Okay, so in the last class we have discussed about the design of a controller. So there are three different types of controllers which are available, which are nothing but the proportional controller, integral and derivative control. And we have seen the independently how they are operating, what is the use of the controllers independently and also with the combination. Okay, so we have seen the proportional controller. So proportional controller is nothing but a KP. Okay, only the KP is there, the gain can be adjusted. So it is a very simple to implement, but it may not sufficient to meet the all design requirements or the performance specifications cannot be obtained by using only proportional controller. So we are going for the proportional plus derivative controller. So proportional plus derivative means this one. So Kp plus Kd into S, which is nothing but the proportional plus derivative controller, so which can stabilize and improve the time response of a system, and it provides more control over the pole locations. Whenever the poles are located, the system performance may be varied. And then if you use the proportional plus integral controllers, tracking of constant reference inputs is possible, and it also rejects the disturbance signals into the system. Okay, and also we have seen the proportional plus derivative and integral controllers, which can operate as a improving the stability and pole placements control and the tracking of a constant reference inputs and the constant disturbance rejection. So all these are the advantages of a controllers. So the same performance specifications can also be obtained by using the compensators. Okay, so what is the necessity of a compensator? So in order to obtain the desired performance of a system, we use the compensating networks, and these compensating networks are applied to in the feedback or feed forward to the system, and it can compensate an unstable system to a stable system, and it is also used to minimize the peak overshoot. And these compensating networks increase the steady state accuracy of the system. Okay, steady state accuracy means it will reduce the steady state error, and in case it can increase in the steady state accuracy, brings into the stability of the system. Normally, whenever we are interested in finding the zero steady state error, so the order of the system is increased, so pole will be added to the system. But whenever the pole is added to the system, order will be increasing, so that the stability of the system will be gets reduced. So this is a major disadvantage of a addition of a pole into the system. Okay, but we can improve the performance by choosing a very small value of steady state error, so that the system may not goes into the instability region. And also here the compensating networks will introduce poles and zeros into the system. Normally in this PI controllers, what you have seen, the KP, if you see the proportional constant, we are adding a KP into the system. Okay, this is only a gain constant. And if you take a derivative controller, the derivative controller is nothing but KD into S. So you are adding a zero into the system at origin. Okay, if you use only derivative control, but it is not the systems to be stable, so you should not add up a zero or pole into the origin. Okay, so here 1 by R Ki by S, this is your integral controller. Okay, so here the pole can be added at the origin or zero can be added at the origin. So these two independently, they are not giving the required performance characteristics, and therefore we are going to use in conjunction with the P controller. Okay, so this is called as a PD controller. Okay, and if you use this with a KP, okay, now this is called as a PI controller. Okay, so this is a PI controller, and therefore now you are adding up a pole and zeros into the system at the not at the origin, but it at the left half of the S plane. So this is similar to a compensating network. Also, it is similar to your PI controllers, which introduces the poles and zeros into the system. So thereby it causes the changes in the transfer function of the system. Due to this performance and due to this addition of a poles and zero, the performance specifications of the system changes. Performance specifications of the system changes now. Okay. So the methods of compensation. If a compensator is connected in series with the plant, then this type of compensation is called as a series compensation. Okay, so it is connected between the error detector and the plant. So this is called as your error detector, and it is connected in between the plant and the error detector. So this is called as a series compensation. Now if it is connected in a feedback across the plant, this is called as a feedback compensation. Okay, and then there is a compensation which is in a feed forward. Here this is a feed forward and this is a feedback. Okay, so here unity value of gain can be added here in the forward direction, and the compensator is connected in the feedback direction. Or also you can also use a combination here, some GC 1 of S, and this is a GC2 of S, GC2 of S. So this value will be connected in a series, and another compensator is connected in a feedback or parallel. Okay, so this can be called, if this is directly taken, this is a forward, so this may be G3 of S. Okay, so this is in the feed forward direction and this is in series. Okay, so this is also called parallel. Okay, then another compensator is connected in a feedback. So this combination of these compensators are called as a load compensation. So these are the different types of compensation techniques. Now, so what are the compensating networks? So a compensating network is one which makes some adjustments in order to make up for the deficiencies in the system. So if you see that the system is having some deficiencies, that means you should have a specified time constant of settling time of TS. Okay, or your percentage peak overshoot will be certain value, and also the velocity are proportional error constants, and also the settling time TS. So these are the performance specifications from the time domain analysis. So if you are lacking in this, if a system is having more peak overshoot, okay, then we need to reduce this peak overshoot to small values. So these are the required specifications of a system. So MP should be less than certain limited value, and your settling time should be less than certain value. So these values can be improved by using a compensating network. And the compensating devices are maybe in the form of electrical or mechanical, electronic or hydraulic, also electronic, also op-amps can also be used. Now the most electrical components are RC filter. So RC circuits, which can be called as a compensating network. And also these networks, these compensating networks are called as a lead network or lead compensator, lag compensator, or the combination of lead and lag compensators. So in our syllabus, we'll discuss about the lead compensator, lag compensator, and the combination with this lead and lag compensator we'll discuss in today's class. Now, so lead compensation. So what is a lead compensation? A system has one pole and one dominating zero. A system has one pole and one dominating zero. the zero which is closer to the origin than all other zeros is known as a dominating zero. So this type of network is known as a lead network. So if you want to add a dominating zero for a compensation in the control system, then we have to select the compensating network. We have seen in the last class we have seen what are the effects of adding the poles and zeros into the system. What are the locations of poles whenever we add a pole in the left half of the S-plane? What is the time response? What is the, if it is added in the right half of the S-plane, how the time response varies, which we have seen in the last class. And clearly in detailedly we discussed about this, and also we have discussed whenever a pole is added to the system, how the root locus changes. So what is the stability of a system? Okay, if you add up a zero into the system, so what is the position of a root locus? All these things we have seen. Okay, we have seen with separately with the time domain and specifications, and also with the frequency domain. Okay, so in time domain analysis, you can easily use the PI controllers so that you can improve the performance of a system. Then, so the same analysis can be done with the compensation circuits. Okay, so these compensation circuits, we have to design it and we have to see the performance specifications of a system. Then when we want to add up a zero into the system, a dominating zero into the system, we need to go for the lead compensation. If I want to go for a dominating pole, we want to add a dominating pole, then you have to go for the lag compensation. So you know that. Okay, so what is the effect of adding a pole? What is the effect of adding a pole into the system? What is the effect of adding zeros into the system? So from that, you can easily understand the importance of adding the poles and zeros. Okay. So now the basic requirement of a phase lead network is that all the poles and zeros of the transfer function of the network must lie on the negative real axis, interlacing each other with a zero located at the origin nearest to the origin. Okay, origin or nearest to the origin. So zero must be located nearest to the origin. Now, so this is the electrical circuit for a lead compensation or lead compensating network. Okay, so in the first branch here, the capacitor and resistor are connected in parallel, and the shunt branch there is a resistor. And we have seen in the first unit itself how to find the transfer function for this. Okay, once again I'm going through this. So the I1, the current through the capacitor, is given by C into d by dt of the voltage potential difference between these 2 points. So here the potential difference is EI. Okay, so at this node, this is a node and this is also another node. So this here also the voltage is E naught. So I is equal to C into d by dt of the voltage difference, which is EI minus E naught. EI minus E naught. And similarly, the current through the resistor R1 is given by the voltage difference EI minus E naught by R1. And we know that as per the Kirchhoff's current law, the sum of the currents entering a node is equal to sum of the currents leaving from that node. So I is equal to I1 plus I2. Then you get the current I here. The I will be equal to E naught by R2. I is equal to E naught by R2. So you equate these two equations, which will give you the relation between input voltage and the output voltage. So by using a transfer function approach, which is nothing but the Laplace transform of output divided by Laplace transform of input, So taking a Laplace transform for this will give you the relation E naught by I naught. So E naught by here, 1 by R2 into E naught of S is equal to 1 by R1, EI of S minus E naught of S plus CS into EI of S minus E naught of S, because it is a differentiation. So you need to take the initial conditions also, but in the Laplace transform, neglecting the initial conditions, so this will be goes out. So your transfer function will be represented like this. So now here we are taking a common parameter, okay, R2 divided by R1 plus R2. So this one, R1 by R2 into R1. So if you take R1 plus R2 common, this will be equal to 1 plus S into R1, 1 plus S into R1 R2 by R1 plus R2. Now we are assuming that the attenuation constant alpha is equal to R1 into C is the time constant. So this transfer function can be represented in a standard form for the lead compensation as alpha into 1 plus S into T, because 1 plus S into R1 into C divided by 1 plus here R1 into C can be represented as T, the time constant T, and R2 by R1 plus R2 can be represented as a alpha. And therefore this is a standard form of a transfer function, so which is having a 1 0 and 1 pole, 1 0 and 1 pole. So similarly here you can also take that PI controller. So PI controller is nothing but it is just a general approximate analysis with the PD controller here. Just I'll take PI KP. If I take common now, this will be nothing but 1 plus KD by S, KD by KP, KD by KP into S. Okay, so divided by, you can also add up one pole here into the system by just taking the value or constant value. So it is similar to like this. So here you can call it as a 1 plus or S plus Z divided by S plus P. So you are adding one pole and 1 0 into the system. It is similar to the proportional PI controller or PD controller like this. So here you are adding a 0. So here the 0 will be located very nearer to the origin, because alpha is less than 1, so it will be having highest value, so the pole will be located away. So the net effect of the system will be having a 0. Okay, so 0 is nothing but which is leading the phase angle. So the above network here, this network is visualized as with a gain of alpha. Okay, K will be taken as 1 by alpha. So the lead compensator, this can be taken as alpha gain. Okay, and the lead compensator is more dominating. Okay, so in the lead compensator, 0 is more dominating than the pole, and because of this, lead network introduces a positive phase angle to the system when it is connected in series. So it will provide a positive phase angle into the system. So if you want to add up the phase angle into the system, if you want to increase the phase margin of the system, so you can add up a lead compensator into the system. So we'll see how to model it, how to design a lead compensator for a given system. Okay, so now here the lead compensator which we are taking here. So here I am assuming that alpha into 1 plus st, this is a 0. So 0 is located here and pole is located with a s is equal to minus 1 by alpha t. So this analysis what I am doing here, some constant k into s plus zc divided by s plus pc, which is a general form of a transfer function of a lead compensator. So which is nothing but s plus 1 by t, s into 1 plus s into t can be represented as here 1 plus st. So we are having a 1 by 1 plus st divided by 1 plus s into alpha t. So I'm taking this alpha t into this side. So you're getting a one pole, one zero and one pole. So here these are located, one minus 1 by t and minus 1 by alpha t. So 0 is minus 1 by t, pole is at minus 1 by alpha t. So the value of zc is less than pc because alpha is less than 1, because r2 by r1 plus r, therefore alpha is less than 1, and therefore zc is the pole having a magnitude, real negative real magnitude will be lesser than pole, and therefore which is located nearer to the origin, and because of this it will provide you the positive phase angle. Now if I want to design this lead compensator in a frequency domain, now we have to replace, always we have to replace s with j omega. In frequency domain we have to replace s with j omega. So for this transfer function, just you write up this alpha into k 1 plus j omega into t. Here j omega instead of j s we are putting a j omega, and here also 1 plus j alpha into omega t, and therefore this constant alpha into k can be represented as a k dash into 1 plus j omega t. So this is a transfer function of a compensator, and now this compensator will have the new value of gc of j omega dash, let us assume here, and the k dash is designed for the first time, okay, for gc dash of j omega. Now so what is a Bode diagram for this? So it is having two transfer functions here. Okay, so the two corner frequencies. One corner frequency is omega c1, and another corner frequency is omega c2. So what is the first corner frequency? 1 by t. Okay, and the second corner frequency is 1 by alpha into t. This is a second, the corner frequency 2. Okay, so first corner frequency, so it is in the numerator term, and therefore below that corner frequency our Bode plot will provide 0 decibels below the cutoff frequency. This will provide the 0. Then after that this is a 0 in the numerator term, so it will provide a positive dB. So this is a 20 dB per decade. So the slope will be now 20 dB per decade, and then after that, so this will having a corner frequency here. This corner frequency is equal to 1 by t. At this 1 by t, your slope will be now varying like this. So how to find this magnitude? The magnitude can be obtained by this 1 plus omega square into t square. This is the magnitude of the system divided by root of 1 plus alpha square omega square into t square. This is the magnitude of your gc of j omega, gc dash of g of j omega. Okay, so when you are drawing the Bode plot, first of all you are taking the first corner frequency, then you are writing this. So it is having a 0 slope up to the corner frequency of 1 by t. Then the slope will be increasing. Then at this instant, now here we are assuming that is 100 into t. Okay, just if you assume alpha is equal to 0.01, so alpha is equal to 0.01 means this will be equal to 1 by 0.01 is 100 divided by t. So at 100 divided by t, again there is a corner frequency. Now your minus 20 dB will be added to the system. So minus 20 dB plus 20 dB, this will be now 0 dB per decade. So this is a Bode plot for a given lead compensator. Now the phase angle is also varying like this, which is nothing but a tan inverse of, the phase angle is nothing but tan inverse of omega t. Okay, so this is a phi will be, the phase angle phi will be equal to tan inverse of omega t numerator term minus tan inverse of alpha into omega t. So you can take up omega is equal to different values. So the phase angle will be various like this. Okay, so this will be increases, and always you see that the phase angle is positive. The phase angle is always positive, and therefore this Lead compensator is a high pass filter and provides phase lead to all sinusoidal frequencies. By observing this, you are learning the positive phases only. Okay, and that's why it is called as a high pass filter. So here this low pass, low signals will be attenuated, and it is allowing the high frequency signals. So it is similar to the proportional controller. The lead compensator rises the Bode magnitude plot at higher frequencies without disturbing the low frequencies. So there is no disturbance. It is not making any disturbance to the low frequency components, and it is allowing the high frequency components. And therefore, the operation of this is similar to the proportional controller also. Now, so I want to find out what is the maximum phase angle for the system here. So when the maximum peak overshoot takes place, and so that your gain margin is varying, and where the gain margin is zero, what is the phase angle of the system? So then what is the phase margin and gain margin for the given system? It can be obtained. So here the frequency omega m at which the lead compensator provides the maximum phase lead. So here this is called as a maximum phase lead. So we need to find out the corresponding frequency, which is nothing but omega m. This is a frequency at which the maximum phase lead occurs. So that point we need to find out. So to do that, we need to differentiate the phase angle equation. We know that the phase angle will be now tan inverse of omega t minus tan inverse of alpha into omega t here. So tan inverse of omega t minus tan inverse of alpha into omega t. So if you differentiate this equation with respect to omega, then you will get the relation for omega where you are getting a maximum phase angle. Okay, so if you do this, so differentiation of tan inverse of omega t is nothing but t by 1 plus omega square into t square minus alpha into t by 1 plus alpha square omega square into t square. This will be equal to 0. So you are going to get a condition that omega is equal to 1 by root of alpha into t. Okay, so here we know that t will be now, this can be obtained from the parameters itself. So t is the time constant of the system, r1 into c, and alpha is equal to r2 by r1 plus r2, r2 divided by r1 plus r2. Okay, so here the frequency is the geometric mean of two cutoff frequencies of the compensator. So which is nothing but 1 by t comma 1 by alpha t. So these are the one corner frequency is 1 by t, corner frequency is 1 by t, and another corner frequency is 1 by alpha t. So this is the geometric mean of this. So this is called as a omega m, maximum frequency. So the maximum phase lead occurs at a frequency of omega m is equal to 1 by root of alpha into t. And then the maximum phase lead. What is the maximum phase lead now? So here we found that the frequency at which the maximum phase lead is occurring. Okay, so this is the frequency which we are finding, which is nothing but your omega m. But what is the phase lead? Phi m. What is the maximum phase lead which we have to find out? So this can be obtained by substituting the value of omega m in a phase angle equation. So the phase angle equation is nothing but tan inverse of omega into t, but instead of omega, we have to substitute this as a omega m. So tan inverse of 1 by alpha into t, 1 by alpha into t, so t cancelled out, so you will get as 1 by root alpha minus tan inverse of, so here 1 by, again this is 1 by root of alpha into tau, so this tau and this tau will be cancelled out, this alpha and root, so you will get this one. So it is a tan inverse of 1 by root alpha minus root alpha. So you are going to get a relation that sine inverse of 1 minus alpha by 1 plus alpha. This is a maximum phase lead. Just you have to remember these formulas, that's it. Omega m and phi m. Okay, so if in an exam explain about and derive, if they ask for the derivation of this phase angle, you have to do this. Otherwise, just you remember this formulas. So the maximum frequency, okay, and the maximum phase lead. phi m will be equal to sine inverse of 1 minus alpha by 1 plus alpha. So the lead compensator provides the maximum phase lead of sine inverse of 1 minus alpha by 1 plus alpha at a maximum phase lead frequency of omega m. And therefore, at this instant, the magnitude, the log magnitude at this frequency is given by 20 into log of 1 by root alpha. So this is omega is equal to omega m. So this is the net magnitude, decibel magnitude at this maximum frequency. Now, so this is about the compensator, lead compensator. Is it clear? So once again, I am going through this. So first of all, we are taking a transfer function of the lead compensator, which is represented as 1 k into s plus 1 by t into s plus 1 by alpha t. By using this, we are deriving the or drawing the Bode plot, and also this is a phase plot, and this phase lead compensator is providing the positive phase angle to all the sinusoidal frequencies. Okay, so this is providing the sinusoidal frequencies, and it is acting as a high pass filter. So we need to design, okay, at which frequency the maximum phase lead occurs in the system, phi m. Okay, at which frequency the phi m will be occurring, we have to find out this. So to do this, I'm taking a phase angle equation. Now I'm differentiating this equation with respect to omega, and then equating this to 0. So you are going to get a maximum phase angle of 1 by root of alpha into t. So from this, you are going to get the phase angle of sine inverse of 1 minus alpha by 1 plus alpha. And also the log magnitude at this frequency is given by 20 log of 1 by root alpha. Now, we need to design this. So I'm going to explain about the design of a compensator, lead compensator. So I will give you the notes, and the same procedure can be adopted for the lag compensator also. Okay, so we need to go for the designing of a compensator. Just in previous topic, we have discussed about the importance and what is the circuit diagram, what is the equations for the compensator. Okay, so here once you get this alpha and theta and t here, you can easily calculate the value of transfer function. Okay, so we'll see how to add up this. So let us see that a plant which is given by g of s. Okay, so this is your compensator normally, and this is your system. Okay, so the plant, this is a g of s, and this is your output. Okay, and there is a error detector here, and it is a unity feedback system. This is your input r of s, and this is your output c of s. Okay, but in this case, he has not mentioned gc of s, only has given the plant. Okay, so directly this is given to you, and he is mentioning about the required transient specifications. Okay, then what are the required specifications? The peak overshoot should be less than 15%, and the settling time should be less than 5 seconds. So if you take up this is a second order system. So for the second order system, this is s square plus s plus. So this is the characteristic equation for a given system, and from this omega n square is equal to 4. So omega n is equal to 2, and 2 zeta omega n will be equal to 1. Okay, and therefore omega is equal to 2. So zeta is equal to omega is equal to 2. So 2 into 2, 4. 1 by 4 is equal to 0.25. Zeta is 0.25. So these are the natural frequency and the zeta for the given system. But here, now for this system, what is the settling time Ts? So Ts will be equal to 4 by zeta into omega n. 4 by zeta omega n. So this will be equal to 4 divided by zeta is 0.25 into 2. So 0.25 into 2 means it is 0.5. So 0.5 to 5 and 48. So this will be equal to 8 seconds. So the settling time for the given system is 8 seconds. Natural frequency is 2 radians per second, and zeta value is 0.25. This is a time domain specification. These are the time domain specifications of a given system. But our requirements was, what are the requirements now? Your peak over should be less than 15%, and settling time should be less than 5%. Okay, so if you here you take 3 by zeta omega n, also 3 by zeta omega n, it is going to be 6 seconds. Okay, so this is with 2% error, and this is with 5% error. So 6 seconds. If you take a settling time is 6 seconds, but what is the requirement here? This is a 5 seconds. And with these specifications, your damping ratio will be 0.15. Okay, so you know that peak overshoot formula is e to the power of minus zeta into pi divided by root of 1 minus zeta square into 100. Okay, so if you take this will be 15%, then you are going to get that zeta will be equal to 0.157, but our value is 0.25. And if you take up zeta is equal to 0.15 and the settling time is 5, so you are going to get the natural frequency of 1.547. So these are the requirements of a system, and these are taken from the time domain specifications. Now, from the frequency domain specifications, the phase margin is 53.172, and the gain crossover frequency is 1.192, and the steady state specifications are 40 kV. Steady state specification means the velocity constant here because of type 1 system. The system is of type 1, and therefore we are going to see that it is a kV. So we need to have a 40 seconds. But for the given system, so for the given system, what is the system here? So this is a system is given to you. For this system, the Bode diagram is like this. The Bode diagram is like this, and from this Bode diagram, we are observing that the phase margin is 28 degrees and kV is equal to 4. kV is equal to 4, and the phase margin, when we get the phase margin is obtained when the Bode plot is crossing 0 decibels. So at this 0 decibels, you have to drop a line here. So this point is nothing but your phase margin. So here, this is like this. This will be minus 140 or 1 like this. So the gain margin, phase margin will be 28 degrees, and this is occurring at certain frequency, and the value of kV is equal to 4. But what are the requirements here? kV should be 40 and phase margin should be 53. The phase margin should be 53, and your gain crossover frequency will be 1.19. So this is a 10.9. This is a 1.19. Okay, this is a 1.9 and 2. So 1.2. Okay, this is a 10 power 0 into 1, and this will be 2. So this value will be 2. So your gain crossover frequency should be 1.2. That means it should be somewhere here. You have to get it. Okay. So these are the requirements of a system. So to get these performance specifications, we need to design our compensator, which is called as GC of S. Okay. Once again, I'm telling you, for the given system, 4 by S into S plus 1, the settling time is 8 seconds or 6 seconds, and the damping ratio is 0.25. Okay, and the peak overshoot is greater than 15%. Normally, if you observe this, If you're using this zeta, you can find out the peak overshoot which is greater than 15%. But our requirements are the peak overshoot of 15% and the setting time should be 5 seconds. And therefore, we need to design the system in such a way that our natural frequency is going to be 1.54 instead of 2 radians per second. Okay, initially this was 2 radians per second. Now, if you add up something to the system, your natural frequency has to be changed and the damping ratio should be changed. Similarly, here for a given system, the Bode plot, if you draw the Bode plot in a frequency domain, it is giving you the phase margin of 28 degrees only, but we need an additional phase margin. Okay, so the net phase margin should be equal to 53.172. So according to these specifications, we need to design a system. I'll see how to design this system. Okay, so now let us use a compensator which is having GC into J of omega, which is equal to K dash into GC dash of J of J omega. Okay, so now let us fix that. This K value can be fixed here. So what is the definition of a KV? KV will be equal to limit S tends to 0, S into K dash into GC of S into G of S. This is your original plan. Okay, GC of S is the plan, and this value will be your controller, so that this value must be equal to 40. KV should be equal to 40. So KV should be 40 means KV should be 40. It indicates that the K dash, the value of K dash must be equal to 10. So KV is equal to 40, but as per our system, so our system is having 4 by S into S plus 1. 4 by S into S plus 1 here. So S is cancelled, S and S will be here. 4 by S into S plus 1. So this S and this S will be cancelled out. So if you substitute S is equal to 0, this is going to be 0. So you will get a value of 4. So K dash should be equal to 10. So this is fixed. Now K dash is fixed. K dash will be equal to 10. So we use this K dash and then we redraw the Bode plot. The value of K must be included into the system. Then we need to draw the Bode plot using this new value. What is the phase margin? So phase margin can be obtained at when the between that, if you draw the graph sheet, it is very clear to you. Directly you can find out that the value of the gain crossover frequency is 6.28. Okay, so here I'm not designing the complete GC of J omega. Just you remember this. This is not designed up to now. Only we are designing the value of K dash. Okay, so only the K dash is fixed according to our value of KV. Given value of KV, we are fixing the value of K dash. Then we need to see the complete transfer function, which is in the form of 1 plus s into t, 1 plus s into t divided by 1 plus s into alpha into t we have to design. Okay, so here we need to find out what is the value of t and what is the value of alpha, so that you can get complete transfer function of a lead compensator. So to again, so the steady state performance is satisfactory because we are assuming that kv is equal to 40. So you are designing k dash, you're designing k dash is equal to 10. Your original system is having a transfer function of 4 by s into s plus 1. Okay, s into s plus 1. So you are adding a value of 10. So your kV will become 40. Then we must choose a compensator that does not disturb the low frequency content, and therefore the frequency response of a lead compensator suggests that it is a high pass filter and provides no attenuation to the low frequency components. And we also required that additional phase margin at the gain crossover frequency to meet the transient specifications. So here we are meeting the steady state specification. Now we have to see the transient specifications. So here the transient specifications can be obtained with the help of the phase margin, additional phase margin, which can be added up. So a lead compensator contributes a phase angle at all frequencies. So this can be used to improve the phase margin of a system. So a lead compensator here. So let us add a lead compensator in cascade to the plant. So which is nothing but k dash into 1 plus j omega into t divided by 1 plus j alpha omega into t. So we have already fixed here. So we have fixed the value of k dash, and therefore we need to find out the values of alpha and t that must be selected to meet the specifications. Okay, so the Bode plot of the lead compensator for different values of alpha is given at the right side here. This can be drawn by using a MATLAB or Simulink software. Directly you can draw it. Okay, so if you take a normal graph sheet, it takes a lot of time to draw this. So for any value of alpha here. Now, so here how to choose the values of alpha and theta and time constant t. So here we required an additional phase angle at the gain crossover frequency. So let us choose omega m at the gain crossover frequency. Omega m is the value should be chosen at the gain crossover frequency. But here the compensator system has a phase margin of 9.04 only. The phase margin is 9.04, but the required phase margin is 53.172. So this is our required problem, phase margin in a given problem. So what must be the value of phi m? The maximum phase lead can be obtained by using the value here, 53.172 minus 9. So this will be the additional phase lead which is required. Additional phase lead which is required. And also choose omega m is equal to 6.28, because at 9.04 your gain crossover frequency is at the gain crossover frequency is 6.28. So it is obtained from the Bode plot. So here we know that the maximum phase angle will be phi m will be equal to sine inverse of 1 minus alpha divided by 1 plus alpha. We know that alpha can be obtained with the analysis alpha 1 plus sine phi m. So you can use the phi m value here because it is a originally nothing but 44.132. So this 44.132 can be added up here. So substitute in your sine value of sine of 44.132, you are going to get the value of alpha. This alpha will be equal to 0.179. So alpha will be equal to 0.179. This what we are getting, 179. Okay, so this value we are getting here from the maximum phase angle. Now we know that the maximum phase lead occurs at a frequency of omega, which is equal to 1 by root of alpha into t, and we have chosen that omega m is equal to 6.28, and therefore 6.28 will be equal to 1 by root of alpha. Alpha is 0.179. So from that we'll get the time constant at t also. So t will be equal to 0.3764. So t will be is equal to 0.3764. Then you can design your compensator as like this. So the compensator GC of j omega is equal to 10 into 1 plus j omega t. So j into 0.3764 into omega. T is nothing but 0.3764 plus alpha into t. Alpha into t is nothing but alpha is 0.179 and t is 0.379. This is going to be 0.0674 into omega. So this is your compensator. So your compensator will be like this. Now you are designing your compensator into the system to get a desired specifications of the system. So this is nothing but your 4 divided by s into s plus 1, s into s plus 1, and here this is a 10 into this total transfer function you can add up here. So this is your original system now with the compensated network. So this is your feedback system like this. This is your output and this is your input. So this is a compensator, lead compensator, and this is your plant like this. Okay. So here this blue line indicates your original system transfer function, and this black line indicates the net transfer function with the compensator and also with the plant, and this red line indicates the Bode diagram of only the compensator. Okay, so this compensator is providing a transfer function like this. Okay, and this black line indicates the original phase angle, okay, of this system. So this block line here at this point, this is crossing here your phase margin. This phase margin will be equal to 43.4, okay, and at a frequency of 12 H. So this is your origin. So because of the phase magnitude contribution of the lead compensator, the gain crossover frequency shifts to the phase margin is the new gain crossover frequency is less than So with this new magnitudes and the new frequencies, the lead compensator can be obtained like this. The magnitude of k is not changing here, but your t value is changing and your alpha value is also changing. So this is your new transfer function of the system. If you draw this, you are going to get a phase margin of greater than 53.172. Our requirement is the phase margin should be greater than 53.172 and your gain crossover frequency must be greater than 1.198. So which is you are going it as a 11.2 here. The gain crossover frequency here, this is a 11.2 and your phase margin is 53.3 degrees, which is greater than 53.172. So this is a way of finding the phase margin and gain margin of a system. Is it clear, everyone? Hello? Is it clear? So I'll take 5 more minutes only, 5 to 10 minutes. I will explain you a phase lag network and a lag lead network. So I'm not going in detail about the designing. I will provide you all these PPTs to you. Okay, PDF, I'll make it a PDF and send it to you so that you can go through this. Is it clear? I will go through the next slide again. Okay, so we will discuss. Is it clear? The lead compensator is clear or not? If you have any doubts, you can ask me now. The lead compensator is clear or not? Okay, so now we'll discuss about the lag compensator. So in this lag compensator, again we'll have a zero and a pole, but this is a pole is dominating here than the zero. So a dominating pole is placed closer to the origin. Okay, so the effect of dominating pole is required, then the type of compensation is known as a lag compensation. Okay, so here this is a circuit diagram for the lag compensator. The series arm only R is there. Okay, and in the shunt branch R2 and C is there. So if you apply the KVL for this first loop, okay, so EI, the applied voltage is equal to I into R1, I into R1 plus I into R2 plus 1 by C into integration of I into dt. And then output voltage equation is the voltage across this term. So E naught will be equal to I into R2 plus 1 by C into I into integral of I into dt. Okay, and then taking a Laplace transform for these two equations, this will give you EI of S and E naught of S. So EI of S is equal to R into I1 of S plus R into I2 of S plus 1 by CS into I of S. So here also this one. So if you apply the Laplace transform and taking a transfer function, which is nothing but the Laplace transform of output signal by Laplace transform of input signal, this will give you R2 plus 1 by CS. Here I of S I will take a common, R2 plus 1 by CS divided by R1 plus R2 plus 1 by CS. So if you take CS common, so R2 CS plus 1 and the denominator R1 plus R2 CS plus 1. So by substituting this, you are going to get this transfer function 1 plus t into s divided by 1 plus beta t into s. Okay, so here the pole, the beta is greater than 1, normally the beta value is greater than 1 because R2 plus R1 by R1, beta is equal to R2 plus R1 by R1, and therefore the value of beta is greater than 1. So the pole is located near to the origin or imaginary axis, and the pole is located away from this. So here in this case, the lag compensator, the pole is dominating, the pole is more dominating. Okay, pole is more dominating than 0. Because of this, it will produce a lag network, and it introduces a negative phase angle into the system. Okay, because it is a positive, this one is positive and this is negative, so positive minus negative, so the negative is more dominating, so we'll get a negative phase angle into the system. So again, the same analysis which you can do it here, s plus 1 by t, s plus 1 by beta into t. Okay, so beta is greater than 1, then you can use the frequency domain analysis, the same analysis what we have done for the lead compensator. Okay, so here this is lead compensator, and the Bode diagram is providing like this because it is a pole, so it is contributing minus 20 dB, so this is a minus 20 dB per decade. Then after that this will be 0. Okay, and the phase angle will be negative, the phase, it will produce a negative phase angle. Okay, so minus value. Okay, so this is a value here, and the border plot will be having a minus 20 dB with the pole because it is having a corner frequency omega c1. Omega c1 will be equal to 1 by beta into t, and omega c2 is equal to 1 by t. Okay, so 1 by beta into t and 1 by t. So here at this corner frequency, and this is another corner frequency, and your phase angle is always varies from the negative value 0 to 0, which is in the negative value, because the tan inverse of omega t, which is a lesser value. Okay, it is a positive value is lesser than the negative, so it is angle will be negative. So the effect of the lag compensation is the gain crossover frequency increases, bandwidth increases, and phase margin will be increased. So the response will be slower before due to the decreasing bandwidth, the rise time and the settling time become larger. Okay, so the phase lag network allows the low frequencies and high frequencies are attenuated, and due to the presence of lag compensator, the steady state accuracy increases. These are the advantages of your lag compensation, and the disadvantages are the speed of a response decreases. The speed of a response decreases because of this. Your settling time and rise time are larger. Okay, so now lag lead network. So with the single lag or lead compensation, it cannot satisfy the design specifications. So for making an unstable, uncompensated system, lead compensator provides a fast response. So lead compensator provides a fast response, but does not provide enough phase margin. So initially we have seen that it is producing only 9 degrees of phase margin. Now we are designing the new system so that it is increases to 59. Okay, so this is a disadvantage of the system. Now our lag compensation stabilize the system but does not provide the enough bandwidth. So we need, if you need these all these requirements, so we need to go for the multiple compensators in cascade. That means lag and lead compensation, which will be connected in cascade. Okay, so this is a circuit diagram for the lead compensator, which is having a parallel combination of R, capacitor and resistor, and the series combination of resistors and capacitors. So if you find out the transfer function with this, okay, you can find it out by applying your mesh analysis and nodal analysis. The transfer function is obtained like this. So E naught of S by E of S is equal to 1 plus S into T1 into 1 plus S into T2 divided by 1 plus beta into T1 into 1 plus S T2 by beta. This is a transfer function of the system. By using this, you can provide the poles and zeros. Okay, so the pole will be located nearer to the origin, then 0, and then 0 and pole. Okay, so this is providing the lag compensation, and this is providing the lead compensation. So if you want to operate this as a lead and lag, so we need a maximum of lead case and than the lag case, so you need to interchange this. Okay, so by adjusting the parameters of the system, you can make that 0 can be made nearer to the origin, and then pole and 0. Like this, you can make it out. So it depends on the network requirement. So here also, this is the lag lead compensation, how we are doing it. Then it is probably providing the 0 compensation. Okay, positive, because of this is a lag. Okay, and this is a lag compensator, so it is having a negative slope and then 0 slope. Then it is making it as a lead compensation, then making it as 0. Okay, so 0, so positive, then 0. So this is a design of a lag compensator. Design of lag. Design a lag compensator. The same analysis what we have done it for the here, stopping here. So do you have any doubts? Tomorrow I will take the class in the afternoon only. So, can I take a class at 9 o'clock? I will take a class tomorrow. I'll start the 15 minutes, maximum 2 hours, at 2.5, 1.5, 1.5, 3 hours. Within 2 hours, 8 minutes and half minutes. Are you listening? Yes. listening or not? So 1 hour 15 minutes, 1 hour 15 minutes. Like that I'll take for the last unit. So that the syllabus